All right, so the next half of this lecture is the most difficult part of our session today. What we are going to focus on today is actually the positive correlation issue of the altimeter. So specifically, let's start with the principle of our barometric altimeter. Earlier, we used a derived formula, right? We said that if we assume a known temperature, and at the same time, we know the reference pressure, which is the pressure at the ground level, B0, then we are responsible for the air pressure at a certain local altitude. Then we can directly calculate, using the air pressure, what the current altitude Z should be, right? Now, under standard atmospheric conditions, with the change in temperature as altitude increases, we can also make this formula more complex to express it. So, that means if, on a certain day, the airplane happens to be flying on a day where the atmosphere perfectly matches the standard atmospheric conditions, then what would the altimeter reading be? How does it compare to the actual value? It should be exactly the same, right? However, such an ideal day basically doesn't exist, does it? So, what do? We need to make an adjustment to the altimeter reading to achieve the desired state. Well, this is known as the altimeter correction issue. So, here, we can see the important parameters that need to be determined, which differ from the standard values. From this equation, what are they? One is temperature, right? The temperature might be different. What else? Another one is air pressure, which might also be different. So, regarding these two parameters, air pressure and temperature, relatively speaking, air pressure has a greater impact, while temperature has a smaller impact. Moreover, as altitude changes, we say that the temperature at high altitudes under ideal standard atmospheric conditions decreases linearly. However, in reality, it might not be like this. And as you go higher, the temperature is also difficult to measure, right? So conveniently, the impact of temperature is relatively weaker. Therefore, when we calibrate the altimeter, in fact, we only need to adjust one parameter. That is P0, which is the reference air pressure. This is the air pressure value at the ground level. And by adjusting this B0, we can input different P0 values accordingly. We can then obtain the true height, Z, or an approximation of the true height. In the actual use of the altimeter, we need to rotate this knob and then adjust our reference air pressure in such a window. This is our specific operation. Let's take a look at how it is mechanically implemented. This altimeter is actually called a sensitive altimeter, not because you have to handle it gently, but because it can be adjusted for the current atmospheric pressure, as the pressure at any given point on the Earth never remains constant. Otherwise, it would always give incorrect readings. Fortunately, pilots can correct this issue. Once the pilot notes the current atmospheric pressure, also known as the altimeter setting, all they have to do is rotate the knob on the lower left side of the instrument until the current pressure is selected in a small window on the face, called the Colesman window. This then realigns the gears inside, allowing the instrument to read accurately. So, the realignment is accomplished by rotating the entire internal mechanism of the instrument. All right. So this is the mechanical mechanism for altimeter adjustment. It's enough for us to know that it has such a mechanical structure. Now, let's consider something more, a bit more complex, which is the specific use of the altimeter setting. We'll introduce this with a problem. Let's assume the temperatures at two locations are the same. If we maintain the altitude, the altimeter setting, and the reading remain unchanged, meaning the altitude read from the altimeter does not change. We then fly from a reference point where the ground pressure is higher to a place where the reference ground pressure is lower. At this point, how should the altimeter reading change relative to the true value? First, let's analyze using the most scientific method. We'll use the formula we just mentioned to directly observe its changing trend. This is the simplest way, right? The most straightforward. So, here we say that when an airplane is flying, we keep the readings constant. What does that mean? That's it. The pressure doesn't change, right? Because we are measuring the current pressure, correct? Then, after substituting P0, we calculate the altitude. Since our wave's positive value doesn't change, P0 also remains constant, right? That's the process of flying. No problem, right? Okay, now let's say we fly from a place with a high reference pressure to a place with a low reference pressure. What does that mean? Without broadcasting the positive value, at this point, the P0 used in the calculation. How does it compare to the actual value? It's larger, right? Because I flew to a place with lower pressure, its P0 should be smaller, but I didn't broadcast it, right? It still maintains the higher value, so P0 carries a larger value, correct? All right, since P0 is higher than the actual value, at this point, what happens then? How about this? How should P divided by G0 be? Does it become larger or smaller compared to the actual value? Thank you, thank you. It becomes smaller, right? Then, speaking of this lone function that primarily uses natural age, is it an increasing function or a decreasing function? It's an increasing function, right? So what does that mean? It means that this value itself will decrease, correct? At this point, there's a negative sign in front. So its increase or decrease changes, doesn't it? So, how should this z be compared to the actual value? It becomes larger, right? Then some students might wonder, why not consider this? This part. Okay, especially since there's also a t in here. Regret returning, regret returning, returning. Could this boundary be a negative number? I can say. I also think some students might say, right, this is the initial temperature. It's the thermodynamic temperature. It doesn't have complex numbers, right? So this part here must be a positive number, correct? M is also a positive number. G is also positive, right? So after analyzing the increase and decrease, we can easily understand how it works. Since the P0 used now is greater than the actual value, the reading of the high number is higher than the actual value. It's also greater, right? So, in many related problems, we refer to this as the reading being higher than the actual value, using the term overread. All right, during the flight, we always hope to maintain a certain altitude while flying, right? As pilots, how do we maintain altitude? We push the control stick forward, right? To what extent does the altitude decrease? We hope that our readings remain constant, right? So at this point, if we fly according to the altitude readings we understand as constant, what would be the relationship between the aircraft's flying altitude and the actual altitude? Let's talk about it. Let's go over it again. Suppose, as we analyzed earlier, right? We haven't verified it yet, but the altitude we read is greater than the actual value, correct? However, we want to maintain a constant altitude for flying. So we push the control stick forward to adjust the aircraft. It goes down until the reading matches the number we originally intended. So, how does this compare to the actual altitude? The actual altitude becomes lower, right? So if we want to maintain the same reading, the actual flying altitude will be lower than the altitude indicated by the reading, as it is currently displayed. This could be a very dangerous situation. Why can we easily draw it out? No. In fact, the altitude we read from the altimeter is actually a different altitude. What we are comparing is the air pressure at the current altitude with the reference position, which is sea level or ground level, right? The difference in their air pressure, correct? Or rather, it's not a difference, but a relative relationship. We use this relative comparison to determine our current altitude, right? Now, let's assume that at ADAD, the reference air pressure at the ground is relatively high. And then we fly to B. At location B, the reference air pressure at the ground is relatively low. At this point, since we haven't made any corrections, we are actually using the air pressure of a place lower than the ground as a reference, correct? So, the altitude we obtain at this point is actually measured from below the ground level, isn't it? Therefore, our aircraft would be flying lower. And at this time, since many places have obstacles. In such a situation, there is a risk of hitting obstacles, right? Therefore, the correction of the altimeter is particularly important. If the weather is bad and your altimeter hasn't been corrected, what happens? It would be easy to collide, right? This is what we refer to as the uncorrected relationship obtained from the reference pressure. After discussing the relatively simple concept of pressure, let's talk about the impact of temperature. Changes on pressure altitude measurement. Let's continue using the relationship we mentioned earlier. Suppose the reference pressure values at two locations are exactly the same. When the barometric setting and altimeter reading remain unchanged, and you fly from a place with a high temperature to a place with a low temperature, how will the altimeter reading change relative to the true altitude? Let's use the previous equation to analyze this. We always measure the true value for P, right? At this point, this P0, as you mentioned, is the same for both locations, so it is also the true value. But what changes? It's T, isn't it? T is a positive number, but then the true value decreases. So how does the reading we get compare to the true value? Compared to the true value, we are higher, right? So, using a T that is higher than the true value in this equation, we say this part is all positive, isn't it? What happens to the height we read at this point? We maintain that our current P is the true value, and G0 is also the true value. The T we substitute is greater than the true value. So how does the height we read compare to the true value? It's higher, right? If we use the actual P, the actual P0 and the actual P, it should be just right, correct? But this time, I substituted a value greater than the true value. Then I got the reading. Wouldn't my reading increase compared to the true value? The height increases. Is that okay? In the latter part, because G0 is the air pressure at a lower altitude, right? This G is the air pressure at a higher altitude, and as you go higher, the air pressure definitely decreases, correct? So, this is a number less than 1. Then taking a logarithm, it is definitely a negative number, right? Any number to the power of 0 should be 1, right? So, if it's less than 1, naturally it is. Not to say that a negative becomes positive, which might not be good. So by substituting a T larger than the actual value, the reading gives a height greater than the actual value. In other words, it still results in what we call an override issue, right? So, further, considering the pilot's perspective, we hope to maintain a constant altitude during flight. So what does this mean at this point? we would maneuver the aircraft to descend, right? In this case, it means that by flying according to the unchanged altimeter reading, our actual flight altitude, compared to what we think it is, the actual flight altitude is. How is it? In various ways. Smaller, right? This is exactly the same situation as before, meaning that if we fly from a place with a high temperature to a place with a low temperature, and if we don't make any adjustments or corrections, we might end up flying lower. So let's review what we mentioned earlier. Under what circumstances can we obtain a true altitude reading? We should only know our current true altitude when the atmosphere meets the international standard atmosphere on a very magical and rare day, right? And since the altitude indicates that there is no temperature overcorrection, our altitude is actually 1 most of the time. An approximation. So, for such a theoretical analysis, we can actually use a more intuitive example to explain it to everyone. Let's still use a pressure measurement relationship to illustrate. Here, we assume there are 3 air columns. So, what is pressure? The so-called pressure is when we place a microcrystalline model on top. Now, the weight of this microcrystalline model is fixed, and the diameter of the air column is fixed. So, at this point, isn't the pressure at the very top also fixed? Right? Now, regarding the relationship of thermal expansion and contraction, with thermal expansion, what happens to the air column? It will rise. It rises and becomes higher, right? So, when the temperature is high, actually, the plane, well, it will be higher. Conversely, when it reaches a place with a lower temperature, under the same pressure conditions, the plane, or this plane model, will be lower. This can also be a way for everyone to understand. Earlier, we used 2 diagrams, and now we add 1 more. We explain the altimeter error using a formula considering the relationship with temperature and the altimeter reading as well as the relationship with changes in reference air pressure. However, in actual flight, no one would slowly think about these formulas, right? It's not practical. During busy flight times, if you have to think about formulas and slowly derive them, you might already be in trouble by then, right? So, do we have a more convenient method to handle this? Remember it. With a mnemonic, high to low, down you go. High to low, down you go. What does it mean? Let's translate it into Chinese. It means when you fly from a place with higher pressure or temperature to a lower one. As long as you don't adjust your altitude and follow the reading as it is, your altitude will decrease. So, when we consider practical issues, once we understand how this comes about, we use this mnemonic. It refers to both pressure and temperature. It's been captured. This makes it easy to remember, right? With this relationship, as we mentioned earlier, the actual pressure altitude reading is rarely a completely accurate value. Only in one situation, when the conditions miraculously meet the ideal general conditions on that day. It is only a true value when it meets the international standard atmospheric conditions. So, what about during our actual flights? There are times when we need specific numbers to be accurate, right? At this point, we need to make a special calibration of the altimeter. So, in what situations do we need a relatively accurate altitude? It seems there are scenarios during flight where altitude is particularly important, where accurate altitude is crucial. Takeoff and landing are one condition, right? Besides takeoff and landing, are there other conditions? Emergency maneuvers. Also, obstacle clearance, takeoff and landing, and what else requires us to have relatively accurate altitude markings? Situations where there are other aircraft nearby, right? These scenarios are quite important to us. Therefore, in relation to these situations, we need to consider the corresponding calibrations. So first, let's consider the first scenario, which is when the aircraft is performing a visual approach flight. At this time, the instrument readings are relatively just a reference. We mainly rely on our eyes. Therefore, during visual flight, we hope that this... After the aircraft lands on the airport, to make it visually comfortable, we hope that its reading should be exactly 0, right? This aligns with our intuitive perception in daily life. Then, when we are flying, if we want to know how high to fly, what do? We generally prefer to use the airport as a reference point, using it to determine how high we fly our traffic pattern. At this point, we need to use the first pressure setting. This pressure setting ensures that when the aircraft descends to the ground, its reading is 0. Alright, so what should this pressure setting P0 be? What kind of pressure should the manufacturer's altitude be? What kind of pressure can make it exactly read 0 when it lands on the ground? Yes, exactly. When P equals P0, Z is exactly equal to 0, right? So, we should actually measure the runway, or more accurately, the highest point in the airport area. To be safe, it doesn't matter if it's off by a little bit, we definitely take the highest point as that's the safest, right? A slightly uneven ground doesn't matter, does it? So, at this point, we have a reference position at the airport, where we measure the air pressure, and then we use this air pressure as the reference value in our entire calculation system. So, when my plane lands on the runway, isn't that the case? The number should exactly indicate 0, right? This way, isn't it more convenient and aligns best with our intuitive understanding? Therefore, although it seems to be used less from abroad to domestically, mainly in the UK during test flights, they use QFE during takeoff and landing. It's pressure resistance. All right. So, what is another situation to consider during instrument conditions? Instrument landing. Many times we cannot rely on visual observation of the outside of the aircraft. At this time, it is important to refer to the aircraft's instruments to read our altitude. Meanwhile, to ensure our relative safety, shouldn't our altitude be above all surrounding obstacles? If our altitude is higher than that, we are safe, right? So how is the elevation on the map provided? The highest area. Relative to which reference point is it given? It's given relative to sea level, isn't it? And the obstacles we need to avoid? What should it be? It should be something relatively close to the ground, right? So the hope is that the closer we are to the ground, the more the reading approaches the altitude based on sea level. So how do we calculate to obtain such a relatively accurate altitude value when close to the ground? Actually, we can make a very simple correction. Didn't we mention earlier how the air pressure changes with altitude? 30 feet up. 100 pascals, right? Therefore, by incorporating this relationship, we can calculate a value. Reference pressure, place this reference pressure into the calculation relationship. So, when we land on the ground, regardless of the actual atmospheric conditions, we can adjust it to a precise value. Wow, so that when we land, the altimeter reading exactly matches the altitude. This is possible, right? So how is this corresponding pressure value, called the corrected sea level pressure, derived? First, we measure the field pressure. Then, using the manufacturer as a reference, according to the relationship of 30 feet per hectopascal, to make a calculation. So in this way, the calculated value is directly referred to as the corrected sea level pressure. And then, we place this corrected sea level pressure into our altimeter relationship. And finally, when we take the reading, we get a value that corresponds exactly to the airport's elevation when the plane lands. This solves the takeoff and landing issue we mentioned because our main reference for takeoff and landing is the airport. However, one requires using a navigation chart and the other does not. Therefore, we choose different parameters. Finally, there's another situation where students mention the mutual avoidance between planes during flight routes. Since each plane takes off from a different location, if they use different reference baselines, wouldn't each one get a different altitude? So at this point, can we compare who is higher or lower? We can't, right? Therefore, we must have a common reference value, right? At this point, we would use the standard pressure, which is the standard atmospheric pressure of 1013.25 HPA, or 29.92 inches of mercury. So, in this way, after inputting this value, everyone has the same reference baseline. Thus, the altitude obtained is called the standard pressure altitude. At this point, we use the term flight level to represent it, where one flight level corresponds exactly to 100 feet. This helps aircraft avoid each other during en route flight. Correspondingly, when we input the local pressure, what we get is called the corrected field pressure altitude. The altitude obtained from the local pressure is called the corrected sea level pressure altitude. Then, the altitude obtained using the standard atmosphere is what I refer to as the flight level, or it can also be called the standard pressure altitude. This is considered from the perspective of usage. Since we cannot adjust for temperature, we need to choose different pressure correction values based on different scenarios. Now, this is purely from a theoretical standpoint. Let's look at it from the perspective of flight. First, let's assume we are flying at an airport with an elevation of 120 feet. Now, if we are performing a visual takeoff and landing, we want the reading on the ground to be 0, right? So, which correction should we use in this case? Okay, let's use field pressure, right? Field pressure. Do you remember what the show code I just wrote before was? QFE, right? How do we remember it? It's not an actual word, but there's a clever way to remember it. F for factory, right? So you can think of it as the manufacturer uses QFE, okay? This is a mix of Chinese and English, not a formal mnemonic method. However, it can help with memory. So let's say the pressure that day is 1008 HPA. All right, at this point, if I say the plane, I want to use instrument flight, as we mentioned. When we fly, we want to know what altitude the plane reads on the surface when it's on the ground, right? We are using instrument flight on the ground, right? Don't forget to share with friends. What do we need to do? We know the elevation of the airport, right? So how do we get this corrected value at this time? First, set the field pressure, then come in. We use field pressure, right? We use field pressure 1008, and then we incorporate it into the relationship we mentioned earlier about the change in air pressure with altitude, which is 1 hectopascal for every 30 feet. So, how should this be calculated? 120 types of high-index airports. How many? Today, are we short of a few sections? Yeah, 4 sections, right? Should it be adding or subtracting 4? Okay, thank you. Add 4, add 5. Should be 101 200 hectopascals, right? It should be added. In this way, when we land on the ground, the altitude we get is exactly 120 feet, which helps us refer to the navigation chart to avoid when the airport's altitude is approximately at this position. Ground obstacles, right? Then, when our plane is on the flight path, what do we need to avoid? It's other people's planes, right? At this time, we need a unified standard, and that's when we use standard pressure. 1613 corresponds to the Q code called QNE, QNH. And how do you remember QNE? QNHN. There's an H here, right? What is H? It's C, right? There's a C, so this is Q and H. Yeah, and how do you remember Q and E? Just erase this. What is this? This is 1, right? This is a 1. And what is the standard? The standard doesn't change, right? So this never changes. It's 1013. During exams, this is often tested. These three abbreviations. This course code is not an abbreviation. What do these three course codes mean? We can use these interesting methods to remember them. All right, so here, then let's consider another question. If on that day, by chance, the weather is perfect and just meets the international standard under such circumstances, what is the relationship between Q and H and Q and E? How about it? They should be equal, right? Why is that? We mentioned the formula earlier, that T, right? That T is very difficult to match with the real situation, isn't it? Only when the standard atmosphere is met that T is correct. At this time, when we substitute T0 back to sea level, the value we get for altitude is exactly the true altitude, right? So at this moment, Q and H and Q and E are exactly equal. They are completely the same. All right, that's all we have to say about this wave. Now, let's have the students take a look at this problem. There's quite a bit of English. So let's simply read through this question together. An aircraft was initially flying in an airspace that conforms to the international standard atmosphere. And then, its indicated altitude on the altimeter is 3,000 feet, using the local Q and H of 1019 HP. Then, the aircraft enters a new air mass, where the temperature is higher than the international standard atmospheric conditions. Yet, if the pressure setting remains unchanged, and the local ground value at this location also remains unchanged, what would be the aircraft's altitude at this time? Please take a moment to think about this question. You have 1 minute. Because when we are flying, we don't have much time to slowly fiddle with formulas. So we hope to develop an intuitive understanding. What should we do? We keep the reading unchanged, the pressure setting unchanged, and then from what kind of place are we flying to what kind of place? At this point, we shouldn't be thinking about things like thermal expansion and contraction. In the actual process of flying, you don't have the time to consider these complex issues. We should use the simplest and most straightforward methods to solve these kinds of problems. Did you cry? When you announced it, right? So is it high to low at this moment? It's low to high, right? So it's exactly the opposite, isn't it? Up, down. At this moment, it goes up, doesn't it? So how should your flight altitude be? Above 3,000 feet, right? During the actual flight process and our examination process, you shouldn't slowly tinker with these relationships anymore. This tinkering is to help everyone establish a scientific method, because in our future work, we will encounter a lot of various kinds of information if we rely solely on simple memorization. You'll turn yourself into a machine. Many times, we need to use our knowledge to judge what is right and what is wrong. Therefore, our classes are not just about telling everyone to memorize things, but about teaching everyone how to acquire the correct knowledge. This is the purpose of our classes. All right, so regarding the fluctuation relationship of barometric altitude, what is another situation that is very relevant to our domestic flights? Winter winter, flying in the north, the impact will be significant. Why? When we are on the ground, we say we use the positive wave value to get it just right, to approximately obtain the elevation of the current airport, right? So, what about during our flight? Due to the weather of the day, it is not a standard atmosphere, right? How will its temperature be? Winter in the north. Especially, it's particularly cold, right? In this case, during our actual flight, it's again a high to low relationship, isn't it? Right? Because the positive value we use is accurate when on the ground, but in the air, it inevitably won't be accurate, right? So what happens when flying in winter? As soon as we leave the ground, it's high to low. We're right about that. In this case, we might need to pay attention to the relative height relationship with ground obstacles. You see, this is the most important application scenario of all the knowledge we've discussed for our actual safe flying. Then there are a few altitude concepts that I hope to clarify for our students. First, there's the indicated altitude, which refers to the altitude we read directly from the pressure altimeter. Next, we have an altitude called absolute altitude. According to our straightforward thinking, absolute altitude refers to the distance from where to where. From sea level to the current position, right? Then there's another term called true altitude. How do we, as straightforward thinkers, perceive it? It's like reaching the other side, right? Okay, that's in Chinese. And note that if it's in English, the two words are reversed. Moreover, this reversal is particularly awkward, isn't it? Inspired by ASA, the VA system seems to be different. We need to thoroughly check its specific standard documents. However, the FA's textbooks and materials are exactly the opposite. Your PHAK is the FA's textbook. And then in this course, we tend to use YASA's materials, which are also closer to the Chinese content, so I definitely prefer to stick with what's closer to Chinese. Pay attention to the corresponding FA system's true altitude. Make sure to understand it thoroughly. You can see diagrams on PJK. It corresponds to the absolute altitude. And then, the English word for true altitude is actually absolutely curious. So what about when we actually fly? What should we do? It's this kind of multiple choice question. What to do? Do you think it's possible? Which one can you tell yourself is Chinese? Play. What should we do? Let's directly talk about pressure. We can actually replace some words to say, in the future, everyone will be a captain, right? Everyone is responsible for the safety of an aircraft. According to aviation law, who is responsible for safety during the flight? Is the ADC responsible, or are you responsible? See, for me. Don't know? The captain bears the responsibility for safety. ATC is not responsible. Understand? So now you tell everyone. Why I specifically want to tell everyone about this is to let everyone know what to do when things might get confusing. We can use some special words, for example. There's a word that corresponds to height. The word hat is just not likely to have this. It's not easy, I think, to confuse. So generally speaking, height refers to the altitude starting from the ground. So in this way, it won't be mistaken. And then, if it's altitude, the word altitude generally refers to the height relative to sea level. So in this way, it won't be mistaken. What other methods are there? we can all switch to some other words. We have a vocabulary. For example, what else can we use? AGL, right? Above ground level. The height relative to the ground. Isn't it something we must know? When there might be such confusion, as pilots, we need to have a plan in mind. What is the most important thing to develop in the background? The skills in your hands, that's the easiest part. In fact, what are we doing most of the time? It's about thinking through plans in our minds, how to handle various situations. That's the truly challenging part. Isn't it a bit different from what everyone thinks? Actually, memorizing the skills in your hands is quite easy. Then, there are two more important ones. One is pressure altitude, noppa. Pressure altitude, as we say, is the standard pressure altitude, which means using 1013 as the reference value. The altitude read from this is the pressure altitude. The last type of altitude is called density altitude. According to the textbook, this is obtained by correcting the pressure altitude with the deviation from isotemperature. And it is used to calculate the performance of the aircraft and an engine. You might recognize every Chinese character, but I guess you don't understand what it's saying. In plain language, what does it mean? It refers to the atmospheric density at the altitude you are currently flying. You then look up this density in the International Standard Atmosphere, table, to find out what altitude corresponds to that density. So, the density altitude you are flying at now is how much? Do you understand? So, it's about comparing the density at your current flying altitude with the altitude in the ISA table. This is called density altitude. It has a significant impact on the flight performance of our aircraft. I hope our students can understand these concepts. Of course, this part is not the focus of our Flight Principles course. It is actually something that will be covered in more detail in your future aviation law courses. Now, we can simply draw a diagram to illustrate a very common situation that does not meet the standard atmospheric conditions. What might we encounter when the aircraft is on the ground? True altitude, and then using the FA system, this is called absolute altitude. So, what is not easy to confuse? Right, it's the ship. It uses a reference relative to the ground. Additionally, we sometimes use elevation, which refers to the height of a specific object relative to sea level. Then, when flying beyond the mainland, what altitude are we concerned with? First is the absolute altitude, which we refer to as altitude, and then there's another one. Or pressure altitude, which is like squeezing toothpaste. Relatively, it's a constant. Reference value of 1013, right? This is mainly used for mutual avoidance in the air. All right, so the above is the most difficult part of this lecture. Let's briefly review what we talked about today. First, we discussed the environment of the aircraft and the physical properties of the air. What do we hope everyone understands? Essentially, it's our formula, which is an extension of the formula we learned in high school. We talked about pressure, temperature, and humidity, right? We used the relationship of molecular weight to discuss the impact of humidity. The impact on air density. We hope that this relationship will help us bring back the formula we memorized in high school and remember the corresponding knowledge content. In the atmospheric layers, one thing we hope everyone remembers is the three parameters at sea level. 15 degrees Celsius, and then what should the air pressure be? 1013, 25. Or you can remember it as 1013, HPA, right, the unit. Then there's also the air density, which you might have encountered less frequently in the past. 1.225 kilograms per cubic meter. And then as the altitude changes, there are two important parameters we hope everyone remembers. 1,000 feet, right? The relationship of 2 degrees Celsius per 1,000 feet. And 30 feet per 1 HPA is something we hope students can remember. The second point is the principle and application of measuring pressure altitude. In this part, we just need to have a general understanding of its principle, and the key point is the fluctuation issue of our altimeter. I hope that through the content discussed here, students can understand how the derivation process of this concept comes about. At the same time, it is most important to remember such a mnemonic and be able to apply it. because it is crucial for the safety of our flights. In conjunction with our actual domestic flights, everyone must remember what to do when flying in the northern winter. Just a single drop. We might be at a lower altitude than what our readings indicate, so we need to be aware of this. All right, that's the content for this lecture. Sayed. Finally, just remember the concepts of altitude fluctuations and the different altitude concepts. It's enough to have an impression of them, as they will be discussed in other classes. That's all for today. Thank you, everyone.